Hey guys, welcome to this week's lesson. This week we're going to introduce a really exciting concept called vectors, and we're going to go over how to create a basic physics simulation using Newton's second law of motion. This is going to create a pretty realistic view of gravity pulling down a character to the ground. The goal of this lesson is to get us to have a basic simulation of basic ground in our sketch. But along this journey, we're going to introduce what a vector is, how to use vectors, and we're going to explore Newton's second law of physics, which I think is really cool because if you've learned Newton's laws before, you've probably looked at it like, when am I going to use this? Whenever is this going to be a thing for me? Well, today is going to be a thing, and we're going to see it in action, and it's going to be quite amazing. So let's go ahead, and I'm going to get my screen up here. And if you're not already in it, get into your environments on StackStarter, and I have it up right here. And this is where we left off. So I'm going to just have some notes in here. We left off with basically two objects on our screen. We have the character up here, which kind of looks like a black sun, like black hole sun, won't you come? Right up here. It's not sitting on the ground yet, but it will be by the end of this sketch. So we also have a ground that is just chilling down here. Nice green ground, kind of a flat, not a lot of grass going on, but it's all good. So our sketch here, we have our setup function and we have our draw function. In our setup function, we are going ahead and using that new keyword to construct a new object. And we're creating two objects here. We're creating a character and we're creating a ground. And then in our draw function, which gets called 30 times per second, we're going ahead and drawing our character and drawing our ground. Now, the blueprints or the classes that we've defined down here for our ground and our character basically just construct and console log out that we're creating a new character and a new ground, and we're drawing either a rectangle or an ellipse at some X and Y position. Now these X and Y positions are going to come in pretty important here. This is really, we're going to start to introduce how to move around these objects. Now, if you guys recall from previous semesters, the ability for us to move things around can be simply us just incrementing numbers, right? So if I go here and say this ellipse lives at 100, 100, which is X and Y, 100, 100, I can just move these over and you'll start to see that ball kind of just go across the screen, right? So I'm just changing the position in this grid to be able to just move the ball. Now, this isn't going to be great for us to dynamically move the ball around the screen, right? We need to now change this as we run the program. But in order to do that, we need to use another concept, right? We need to, instead of having these fixed values in here, right, we need to put them in a variable and then change those variables. Now we could do that. We could just make an X position or Y position variable and change them and then maybe test if we've hit the ground. Or we can use a different concept. We can use this concept of vectors. Now, what is a vector? When I say vector, what do we mean by that, right? In many ways, a vector is very similar to an X and Y coordinate, but it's the way that you think about them that makes them completely different. So let's jump into, I have a little prototype here. Just make sure my recording is still actually recording. Okay. I made the mistake of making my shortcuts for OBS Studio something that took me off, which screwed me up a couple times. So we have this little sketch here that shows an X and Y coordinate system, right? So we have this X axis, which is your horizontal plane, and we have our Y axis, which is our vertical plane. And we're talking just 2 dimensions right now. We're not talking about 3 dimensions or beyond. Keeping it simple in 2 dimensions. Now, this is a little different from what I've explained a P5, oh, really an HTML5 canvas is, right? If we look at our sketch here, this is an HTML5 canvas, the origin point of an HTML5 canvas is in the upper left-hand corner right up here, right? So that's 0, 0, and everything is kind of grows from there here. But the way I'm illustrating it here, the origin point is in the center of the grid, right? A lot of times we call this a Cartesian grid in mathematics, right? So when we talk about a point on a Cartesian grid, right, we talk about, we could take this point, maybe put a point out here, and say this point out here is something like, let's move it a little closer because I want to do an operation on it in a minute. Say this point is, I don't know, what do we have here? 1, 2, 3, 4, 5, 6. We'll say it's 6. We'll move it over a little bit here. There we go. We'll say it's 6 in the X position, and we'll say it's, I don't know, 8 in the Y position, right? So this point represents a place in space that is 6 and 8, right? Now, I need to back up a little bit and talk about what just a single number represents in this environment, right? So if we go back to our code here and just kind of comment some stuff here, if we say the number 6, or we say the number 6.5, or we say 0.03 or 0.04, or 6, 4, 3, right? Anything here. These numbers that we're talking about, we can call them scalar numbers, right? These are scalars. Scalars are basically just a single value that we can use to scale different other numbers, right? Or other objects in our system, right? So you think about scaling a number, we could say, I want to take 6 and I want to scale it by some scalar. So I could say 6 times 2 equals 12. So I just scaled it, right? And that could go in the other direction as well. If I want to say 6 divided by 2, right, we would say 3, right? So we can use these numbers to do basic math operations against other numbers. That is a scalar value. Now, when we talk about a vector, we're talking about something different. We're talking about really something that has what we call a direction and a magnitude. Okay? What do I mean by that? We can think of a vector as an instruction for an operation where we're, say, visualize yourself maybe sitting on a 2D plane. That's where you live, right? It's like Edward Abbott's famous book, Flatland, right? You're sitting on a plane and you live at this point. This is your home, 0, 0. That's where you are. Now you need instructions on how to get to this point in space, 6, 8. You need a GPS system, right? Whip out your iPhone, whip out Google Maps, type in that 6, 8, which is the address you need to go to. And what it's going to do is it's going to draw an arrow from, let me draw this arrow from here to here, right? And let's make this a little thicker. Whoa, not that thick, right? So now that little GPS system that you just put in, I'm sitting there at 0, 0 at my home, and I just plugged it in and said, okay, this is how you're going to get there. You're going to have to move in the direction 6 with a magnitude of 8 in order to get to where you need to go. So the vector represents some type of transformation of your current position to get to some other position in space. Really important to understand that. It represents a transformation, not just a point in space. It represents a way for you to transform to a new point in space. And it has what we call components. When we're talking about a two-dimensional world, there are two components, right? There's the X component and the Y component, and it represents the direction and magnitude, right? In this case, the direction is pointing kind of up into the side, and the magnitude or the length of this arrow is a length of 8. Okay? So when we think about it that way, think about we are fixed at home, we haven't moved anywhere yet, and in any place in space, we could take this point anywhere in space. Say we go all the way out here, right? And this is some other point in space. I won't say what point it is because It could be anything really. But if we wanted to then get there, all we would have to do is draw a vector to that place. And now we have the actual directions to get there, right? And now the same thing you can do with vectors, you can do, same thing you could do with scalars, you could do with vectors. So a scalar, you can multiply them together, you can divide them, you can add them, you can subtract them, right? These are all basic mathematical operations that we all know and love, right? We can do the same with vectors. Now this is how you would visualize it with vectors, right? You're basically putting together different paths or different directions and magnitudes. So say for example, let's make this come someplace a little closer so it all fits on the screen here. I'm going to grab this vector and I'm going to move the vector, say someplace closer, and let's put it someplace up here where we're just working with positive numbers to keep it simple. So say for example we go to this point here, and this point represents let's say 4 and 2. Okay, now this isn't to scale, but it's okay, right? So if we wanted to now add together these two vectors, where would this take us? How would our path change, right? So if we took this vector and this vector and add it together, what would happen is this vector would then be moved right here, and that would take us to another point in space here. And that point in space would be, if we take these numbers, what do you think this point in space would be? Just like adding two numbers together, it would be 10 and 10, right? Oop, if I can type this, right? 10, comma 10. Let's move this out a little so you can see that. Right? All we did was we added the components of the vector together. So 6 plus 4 is 10, and 8 plus 2 is 10. So now we have this new path. And this is the same as having this vector starting from your origin point going all the way to 10, 10. You see why that's the case? So now we just have a direct path to 10, 10 instead of adding these two together. And we're going to see this play out as we start to play with vectors and how we can use this to really think about motion in a different way. Now this is super important, and it's really the basis of a whole field of mathematics called linear algebra. Super interesting concept, and vectors really play a pivotal core role to the understanding of a lot of the principles that exist within that discipline. Other constructs like matrices and things like that come into play. Now we use this technology on a daily basis, right? Our GPUs in our computer systems are literally optimized to do operations on vectors and matrices in a very, very highly efficient fashion, right? Teams of people are working on computer chips that are designed to do these types of operations, vector operations and matrix operations. And they really are pivotal in computer graphics. Computer graphics use these all over the place, right? All of the 3D engines that we use are using linear algebra concepts to be able to create and simulate environments, motion, and things like that. So why am I bringing all this stuff up? So why am I bringing this up is because we're going to now think about motion in our system here using vectors instead of just using incrementing values. And that's going to enable us to now use this and create more of a physics simulation, right? So let's go ahead and let's, instead of, I'm not going to jump right into some of the physics stuff, but what I'd like to do is I'd like to just make sure I'm still recording the screen. Yes. And we'll see that pop up a couple times because I want to make sure I'm not accidentally just going right to my face and you don't see anything. So this character here is being drawn at 100, 100. That's where we live here. Let's change this character's position to use a variable. But instead of just saying, hey, you know, something like this, I could very simply say this, right? This dot xpos equals 100, this dot ypos equals 100. And we can go here and just say this dot xpos and this dot ypos. And this will literally give us the same exact result. Nothing changed. And I could do the same thing here and move this bad boy over. You're going to see him starting to move over, right? Same exact thing we're doing, but we now have the position in some variable. And if we wanted to see it automatically move, now we can manipulate this position by just incrementing it, right? We can move it by 1, and now we'll see it animate across the screen. Or if we wanted to see it go down the screen, we could just say y position plus plus, right? Now, that's all well and good. We can totally do that. But let's try to do this using vectors. And P5JS luckily has the core concept of vectors. So if we go ahead and go to p5js.org and we look for Createvector, this is a function that basically creates a vector and returns to us a vector object. Now the vector object has a bunch of capabilities on it for us to do things like I illustrated here, being able to add vectors together and do these types of operations, right? A lot of different operations on a vector that we can do, right? And this is kind of a cool little sketch just illustrating basically exactly what I just illustrated in that plane, where the origin point is fixed, but wherever my mouse is, it's drawing a vector to our mouse, right? And I would encourage you guys to actually try to run this sketch. This is a really basic sketch to illustrate what a vector actually is. So vectors in P5JS do support up to 3 components. So we do have the X, Y, and Z components. We're only going to be working with the X and Y components right now. And what we could do is we could just simply call Createvector, right? So let's go back to our code here. And instead of saying xpos and ypos, I'm going to say pos, this dot pos equals Createvector, and I'm going to say it's going to live at 100, 100. So I give it the components, the x and y components of the vector, and it returns into this variable. So this variable now is an object. The type of the object is a vector itself. And now what I could do here is I can access the components of that vector by saying this.pos.x and this.pos.y. Now we're going to get the same exact result. So we keep doing it a little bit differently, but we are getting the same result, right? Now I can do the same thing here. I can go ahead and move this and you'll see the ball start to move to the side, right? That's all working. All right, so now we have this position expressed as a vector. And we can use that vector here to draw our ellipse at a certain point in space. Okay, that's cool. We're getting someplace here. But we want to make it a little more interesting, right? We want to actually get this to get pulled to the ground. Now, why did I go ahead and introduce this idea of a vector? I did this because we want to start to talk about Newton's second law of physics. This is a good one. Now, this is a very famous formula. It's very much like, you probably heard it just as you heard Einstein's E equals mc squared, right? So let me just go up here. Newton's second law of motion excuse me, states that the following. All right, let me get to it here. I'm going to make this a little bigger. It states that F equals M times A, right? Or if you see it, more traditionally, it's just F equals mass times acceleration, right? I'm going to write it with the actual star there, so it's explicit. So force equals mass times acceleration. Now, let me just make this a little bit bigger. This is Newton's second law of motion. Now, typically you would look at initially, right? Unless you studied this stuff, you would look at this and say, that's cool, but I really don't even know what that is trying to tell me. It's probably some crazy complicated thing that I'm never going to understand. And in many cases, a lot of people stop right there, right? And they're just like, okay, that's cool. Newton had a cool second law. He came up with it in like, hundreds of years ago, and it's cool. It turns out that this simple formula, in many cases, approximated a lot of really natural phenomenon for many hundreds of years, and it still does today, and it powers a lot of the different interactions that we have in a lot of digital systems today, even today, right? There's a lot of other techniques, there's more accurate ways, quantum physics came up and did things at a grand scale, at a small scale, but Newton's formulas here, specifically this one, is still very much in use today, and it's a good one to kind of study and apply as we're going to do today. So what are we saying here, right? And it's probably good for me to bring this up too. This is the Nature of Code book, which I keep referring to, which, Daniel Stiffman does a great job with all of this stuff. And I draw a lot of my inspiration from this work that he's done, right? And I do link this in our curriculum here. Encourage you guys to read this chapter about vectors, right? It goes into much more depth as to what I just described. And it does use processing, which is not P5. It's the same exact concept. So you should be able to see this syntax and read it. But it is slightly different syntax from the JavaScript that we're using. But he does, and I think he does someplace here. Oh, it's probably in forces. There we go. In chapter 2, he goes into forces. And Newton's first law states an object at rest stays at rest, and an object in motion stays in motion. So we're going to see that come at play in a minute, right? And the second law, where's the second law? Pretty sure it posted. Oh, here we go. Newton's second law. Force equals mass times acceleration, right? So that's cool, but how are we going to use this, right? Force equals mass times acceleration. So we're not really talking about mass. We have no idea what acceleration means. And what is a force? What is going on here? How are we doing this, right? So before we actually dive into exactly how to use this, let's go ahead into our code here. And we're going to need a couple of other vectors to be able to describe motion in our system, right? And it's not really stated in the formula here, force equals mass times acceleration. But what we can do is we can, if we don't really need to calculate the force, right? But in order for us to move something, we do need to accelerate it, right? So in order for us to get the acceleration, we could do a simple mathematical kind of operation to bring the mass over to the other side of this equation, right? So if we divide both sides by m, we get this, right? So I'm going to go ahead and copy this and paste this here. We get this. Right? Or another way to write it is, and I think a cleaner way to write it is to say acceleration equals force divided by mass. See what I did there? I basically, and I don't have a good way to illustrate this in this sketch, but I divided both sides of this equation by m. The m's canceled out on this side, and the m's stuck around on the other side. So we're left with this, which now, this is the same exact formula, but we are looking at it in a different way. We're saying that we want to calculate the acceleration given some force and some mass. So we can now calculate acceleration if we have those two pieces of information, right? Now, one other thing I want to mention with this formula, notice how F is capitalized here, right? And in many cases, that symbolizes the fact that the force is not a scalar value, right? The force, in many cases, is a vector, right? It's a vector. So it's something that gives us a magnitude and a direction. And we're going to see that in a second. So if we have the acceleration, what we can do is we can actually add the acceleration to what we call a velocity. The velocity is then going to be the incremental change in position, right? Think about a car, right? If you're in a car and you press the gas, right, your car is going to accelerate. And as it accelerates, its velocity is going to increase. And as its velocity increases, its position on the road is going to get faster and faster and change faster and faster. So in order for us to think about motion, motion really comes in these three parts: the position, the velocity, and the acceleration. And they're all interconnected, right? The position is changed by the velocity, and the velocity is changed by its acceleration. Really cool stuff, right? So we can calculate the change in a system by getting the acceleration, adding it to a velocity, and then adding that velocity to the position. So what does that look like, right? So we can think about velocity and acceleration. We can actually think about all of these things in terms of vectors. So let's go ahead back to our character here. And let me just put this here. Let's go ahead, let's define two more vectors. We're gonna say this dot acceleration, or just ACC, equals create vector 0, 0, right? This is kind of playing on Newton's first law, which is an object at rest stays at rest, right? We're not giving it any acceleration right off the bat. And I'm going to say this dot vel for velocity, create vector 0, 0, right? We're not going to give it any velocity and no acceleration. So our object is not going to move at all at this point, right? It's not doing anything. Now, let's go ahead, just to stay consistent with the Newton's second law, we're going to say this dot mass. So we're going to give our character, not max, mass. We're just going to give it a mass of 1. Okay? So our object just has a mass of 1. Cool. So now we have a position, we have an acceleration, and we have a velocity, right? And let me just go ahead and I'm going to comment these all nice. So we have our position, our acceleration, and our velocity. Velocity. We can spell it right. Awesome. All right, so now we have that in place. Now, in order for us to move this object, we need to do something here. So I'm going to go ahead, actually, I'll do this before I do any of the drawing operations. So we're going to do it up here. And we now need to do some calculations here, right? And in order to do this, we're going to basically use Newton's equation here. And we're going to say, oh, you know what, too? We need something else, don't we? We need something else. I'm just looking at some notes here. We're missing something from this equation, right? We don't have our force. So essentially, everything in this equation, the force and the acceleration, even though the acceleration is not capitalized, is actually a vector. So we have a vector here, we have a vector here, and mass is a scalar value, right? So we do need to have some type of force. So I'm going to go ahead and also create another vector called force. And we're going to say that the force, there is no force right now. Okay, so there's no force. But now, instead of doing some calculations, let's use good old, and it is old, Newton's second law. And here what we're going to do is we're going to say this dot acceleration, right, and is going to equal to this dot force, right? And we're going to do this dot divide this dot mass. Now, the reason why we did this, right? Instead of doing this dot acceleration equals this dot force divided by this dot mass, right? Which is how we would typically do it with scalar values, right? But remember, this acceleration and this force, they have components. They have an x and y within them. So we need to basically peer into the actual vectors and then do the operation. We can do this ourselves manually, but the P5 vector class has methods that are nice, convenient methods that we can call that allows us to do these divisions for us. So basically what this is going to do is it's going to divide all of the components within this within these vectors by this scalar value. And this right here is literally Newton's second law of physics. This is kind of crazy, right? So we have this second law of physics, and we wanted to look at, say, a P5 vector reference here. You can see these are all of the methods. So we have subtraction, we have multiplication, we have division, we can set magnitudes, we can square root the magnitude, we can cross multiply. There's a lot of different operations that we can do on these vectors. So in this case, we are dividing. Now we're going to do a couple other ones, right? We're going to now take the acceleration, and we want to add the acceleration to the velocity. So we're going to say this dot velocity dot add this dot acceleration, right? Boom. Oop. And not val. We're going to say this dot vel add this dot velocity. Now our ball isn't moving yet, right? Now we need to add the velocity to the position. So we're going to say this dot position dot add this dot acceleration. Okay. Now it's still not going anywhere because it won't, because remember, an object at rest stays at rest, right? We could now give it maybe some acceleration, right? We can give it acceleration by maybe changing one of the components in the acceleration, or we can maybe change one of the components, better yet, in the force. So we can apply a force to our object. Now, say for example, this Createvector, remember it has x and y. I'm going to go ahead and give it a force of 1 in the y direction. So it should be pointing down. Let's go ahead and apply that force. And now look at that. The ball starts moving down. It's kind of slow, right? And it's just going to keep going. And bye-bye ball. It's gone. Now, that's not very interesting, right? It's doing the same thing that we did by just simply incrementing y, but with more code and more complex. So what gives here, Professor? Why are we doing this, right? This now gives us the capability to now build actual physics simulations that allow us to pull together different types of forces in our environment, right? So say, for example, our ground has gravity, right? So let's go up to our ground here and let's give our ground some gravity. So gravity, you can think of gravity, right? If we go back to our reference here, right? And we have this, so we have a ground here, right? So we'll go ahead and actually, you know what? Let me go back to this. Where's my other layer here? I thought I had another desktop here. All right, well, I was going to use the other prototype, but it's all good. We can use it right here. So say, for example, we have our ground, right? We have a ground right here. Say this is a ground. We'll make it green so it looks like a ground. Nice and green. There we go. Now, if ground has a gravity, that means there's a force or a vector that is going to pull down objects, right? So the force would look like this. It'd be pulling down like this, right? There'd be this force pulling down objects above it, right? So gravity itself is a vector, right? It's a vector with only a y component in this example, right? Because we're pulling straight down. So what we can do here is in the ground itself, we could say this dot gravity equals Createvector. And we're going to say 0, and what did I do in this example here? we'll make it 100. We'll make it actually pull it down pretty hard, right? Now, in order for us to apply this gravity to our character, we need a way to do that, right? We need a way to now apply a force to the actual character. So I'm going to go ahead and right below our draw function here, I'm going to write a new function called apply force. And apply force is going to take a value as a parameter. The value is going to be f. And now here, all we need to do is take this dot force and add f to it. That's it, right? So now we can apply as many forces as we want, and it's going to go ahead and add it to this vector. Now, in order to actually apply this, we need to go back up to our setup function here, and after we create the ground, I'm going to say character dot apply force, force, and I'm going to give it ground dot gravity. Right? So now we're applying that gravity force. Now if we go here, oh, look at that, the ball's already gone. Whoop, look at that, it's going to fall really quick. Let's go ahead and change this to just 10. Ooh. And it goes away. Ooh. Now it is actually accelerating to the ground, and we can't really see that too well because I'm going to lower the diameter a bit, and I'm also going to I'm not going to redraw the background each time. That's pretty constant. So there's a constant acceleration there, right? So the acceleration is constantly growing. Now what we can do is, in order for us to maybe make it a little bit more of a simulation, we can what we call damper the velocity. So what we could do is we can take the velocity here and we can multiply it by some small value. So we could say at each frame the velocity is now going to be decreased. Oh, not multi, just molt. That doesn't really look much different here. Let's go ahead and make this point. Let me make it here. 0.1? Yeah, 0.1. Well, that's not really changing the game too much there. We don't have to play with that, I guess. Play with that another time. Velocity to add acceleration. Oh, you know what I'm doing wrong? I see what I'm doing wrong. I'm like, why is this? This should be constant. Here I'm saying position.add acceleration. I want to add velocity to that. Now, there we go. See how the ball starts here, then the next frame it's closer, it's kind of close, and then each frame it accelerates. This is, we can now see that the ball is actually accelerating towards the ground, right? And we can see that because at each frame the ball is slightly different from the previous frame, right? So we have this accelerating ball going to the ground. We have acceleration, which is kind of cool. So with that being said, now let's go ahead. I'm going to go ahead and make gravity a little bit weaker. And boom, now we can see that much better, right? We start here and now we're accelerating towards the ground, right? Now we can go ahead and we can actually apply all different forces to this now, right? So say, for example, we wanted to apply, say, a wind force, right? We can create a wind force by saying let wind equal create vector, and we'll make the wind force blow towards the x direction. So we could say the wind force is 5, 0. So x is 5, y is 0. And then we could say character dot apply force, say wind. Now we're going to see that bad boy blow, right? But it still has the gravity pulling it down. So if we make our wind a little bit less strong here, and we'll make our wind just 2, you can see that the wind is kind of slowing down a little bit, right? So we can make it even smaller. We can go 0.01, right? Actually, that's too weak. Yeah, you see that wind kind of pushing it there, right? So that's kind of cool. We can kind of accumulate together forces against our object in order to make it move in different ways. So this is an example of using vectors to create motion in our system and leveraging Newton's second law of physics to do so. Pretty cool stuff. So I'm going to go ahead, I'm going to get rid of this wind force. And now the last thing I want to do here is I want to try to get this ground to react when we hit it, right? And we actually did this when back a couple semesters ago, we actually did the DVD logo project, right? We worked on bouncing around the DVD logo on the corners of the screen. And it's basically the same logic, right? We're going to use a conditional statement in order for us to now detect whether or not we hit the floor or not, right? So we can do that right within the character itself, right? So we could say, and there's a bunch of different ways we can do this, but I'm going to kind of do this in a kind of a crude way here. I'm going to say here, let's go ahead and say if the this dot pos dot y is greater than or equal to the ground dot pos dot y, right? Then we're going to say this dot pos dot y equals the ground dot pos dot y, right? And we're manipulating these components in the actual vectors here. And then importantly, we're going to say this dot velocity dot y times equal -1. Now we're doing that because we want to now move it in the opposite direction. Now we're doing something wrong here. So ground, this dot. Oh, we still have this in here too. We got to get that out of there. Why possible that we're not using that anywhere, but we don't need it. So I'm going to get that out of there. And let's go ahead and open up our console here. Oh, you know what? I never created a position vector for our ground. So we need to do that. So we need to say this dot pos equals create vector, and the vector is going to be x position is going to be 0, and the y is going to be window height minus 100, right? Now we have that position, boof, look at that, boof. It's now bouncing on the floor. And what we could do is, to see that a little bit better, we can now draw the background and redraw the background each time. Look at that. Doof, 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 doof. Now eventually, because of the way that the math is working out, the ball will stop on the ground. That looks pretty cool, huh? It looks actually pretty realistic. Now, I also want to use this position though when we're actually drawing the ground. So here I'm going to say rectangle this dot pos dot x, and then this dot pos dot y. And now I just realized I kind of wanted to zoom into this code a little bit. Hopefully you guys are seeing this okay through the video. If not, please shoot me an email and let me know, and I can give you guys some of the code here to follow. I just zoomed in a little bit there. Hopefully that helps. So we have now you can see this bowl is eventually going to come to a stop. Now you're going to notice something here. Let's make that bowl a little bit bigger. I'm going to make this bowl, instead of 10, let's make it 50. Right? And when the bowl actually stops, you're going to see something. It's going to actually sit not on the floor itself, but kind of chilling in the middle, right? And you'll see why this is in a second. But once this stops, and look how this kind of, it's just kind of coming to a stop here. It's bouncing on the floor. Now it stops right in the middle. The reason is that the actual X and Y position of the ball is in the center of the ball. So for it to sit directly on the ground, we need to basically test minus the radius of the ball, right? So let's go ahead and just quickly do that, right? I'm going to go ahead up here and I'm going to say the mass, and right under the mass I'm going to say this dot radius equals, say, we'll make it 50, right? And then we'll make the ellipse, we'll say the size is going to be this dot radius times 2, right? Because the diameter of a circle is 2 times its radius. So we're going to make that ball basically 100 pixels, right? Now, instead of testing whether or not the X position is greater than or equal to the Y position, we're going to say the Y position of the ground minus this dot radius. Whoop. Right? And then when we go here, it's gonna bug out here because the fact that we need to say the position is now going to equal to this minus this dot radius here, right? And now when it stops, we should see that it's going to be hanging out right on the surface of that ground. And eventually it will stop. Boom, 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 boom. And there we go. It's just hanging out right on the floor. So I think this is probably a logical place to stop right now. We did a lot in this lesson, right? Kind of jumped around a bit. Hopefully you guys were able to follow along. Just to kind of recap real quick what we did. We talked about vectors, what a vector represents, right? A vector represents some type of transformation operation from going from one place in the world to another place. Think of it as an arrow that has a direction and a magnitude. We then used vectors to communicate and create a position for our ball. We also used it to create a velocity and an acceleration. And then we also have a force in there as well. Then we used Newton's second law of physics, which is force equals mass times acceleration. We've modified the formula a little bit to just express it in terms of the acceleration by saying the acceleration is equal to the force divided by the mass. In this case, we're really not using mass too much, right? Because we made the mass equal to 1. Anything divided by 1 is itself, right? So it's really not even a consideration here. We're really using it as accelerations equal to the force, which is kind of a simple way to put it. And then we're calculating that acceleration, we're adding it to a velocity, and then we're adding that velocity to the position. And by doing that, it creates this really cool kind of simulation of gravity and a ball falling towards the ground. Now, what we did was we actually made the gravity, we defined the gravity within the ground itself, and then applied that gravity to the character through a new method we called apply force. Which then created this. Now, using this technique, we're going to be able to build from here to do things like jumping and moving and things like that. We're going to be able to apply different forces to our character in order to move it around the world. So in the next lesson, what we're going to do is we're going to actually start to extend on these concepts to be able to move this character around the world. Okay. Now we may even bring in our own, or not our own, but a different physics library to achieve a lot of this stuff. Or we may just kind of continue to build on this. Haven't really decided which direction we're going to go in here, because this could get pretty complicated pretty quickly, and I don't know if I want to get too deep into that. But I do think you guys should be able to get to this point. So really, at the end of this lesson here, what I'd like you to do is basically follow along, get the sketch working exactly how we see it here. Where we have here's the ground object or the blueprint to create that object. You can pause the video right here to take a look at that. And then here is the character, right? The character is a little bit bigger. The character is what implements a lot of the actual Newton's second law here. So pretty cool stuff. I hope you guys got a lot out of this. I'm going to go ahead and link up not only this video, but also the Nature of Code chapter. I'm going to also link out to some of the videos that Daniel Stiffman did on this topic. He does a great job explaining this stuff. He goes into it in a bit more depth in a series of videos. So if you guys are interested in exploring that, definitely recommend checking him out. Mega talented dude, teaches a similar course at NYU. And yeah, any questions, you know where to find me. Shoot me an email, and I look forward to working with you on this. All right, guys, thanks.